Hello everyone, you're welcome to MERSTHUB Mentors, and I'll be taking you through a new series, and this new video series is Python for chemical engineers. So this is specifically targeted at chemical engineering students, teachers of chemical engineering faculty, and practitioners in the industry. Talk about problems such as optimization, we'll look such as curve fitting, look at problems as reaction, and see how we can use Python to solve this problem. First, we know what optimization talks about. Okay, it's a systematic way of trying to modify a process in order to improve its performance according to predetermined criteria. And such criteria could include increased yield, reduced cost, reduced waste, lower energy consumption, and improved safety. All of these criteria actually form or constitute what is referred to as the objective function. So in this video, and all of the problems I'm going to solve in this video are the references. They are all taken from optimization of chemical processes by Edgar Himmelblau and Latzen, second edition, and also Elements of Chemical Reaction Engineering by H. Scott Fogler. So I just give a pictorial view of the various kinds of constraints we have in optimization problem. We have the linear inequality constraint, we have the linear inequality constraint, and then we have the linear equality constraint. All of these constraints put together help us to define the feasible region, which separates the infeasible region. Under the feasible region, the problem is optimal, or we have an optimal solution, as we say in chemical engineering. So first, we have to define the problem, which is the objective function of the problem, and here we want to minimize. And if we have to optimize, all we need to do is to minimize the negative of the optimal optimization problem. So we have subject to one, equality constraint and inequality constraint. So in a problem, we can have just all equality constraints, or we can have all inequality constraints, or a mix of equality and inequality constraints. And mind you, here x is a vector of variables, okay, which could range from 1, 2, 3, 4 until n. So n number of variables can be taken. So to solve this problem, or to solve problems using Python, first we need two packages. We need NumPy, and then we need SciPy.optimize. We need the SciPy package and the sub package optimize, where we'll import minimize. So we have this imported to our namespace. First problem here is to minimize 4x1 minus x2 minus 12. In other words, get the values of x1 and x2 that will give the minimal value of this function. Okay, and this is subject to. Now, let me quickly make a caveat here. This optimization problem here is actually called constrained optimization. In some optimization problem, we refer to them as unconstrained optimization problem. We're still going to look at that very shortly in this video. So subject to, I have an inequality constraint here and two inequality constraint and a non-negativity constraint. This negative constraint here is simply saying x1, x2 variable must always be positive. So the solution, first we categorize x because we have two variables as x1, x2. Because Python indexing starts from 0, so we'll define the variables x using 0 for x1 and 1 for x2, the pointers. So here I define a function as a lambda function. You can as well define the function using the conventional way in Python using the keyword dev. And next, I will define my constraints, which will be defined as dictionaries of a tuple. So I have the first dictionary carrying the type inequality, the function, I'll pass in the lambda function, and then the next one and the next one. So I have one equality and two inequality. So I'll pass them right in the same way. Now notice here that the two inequality constraint has greater than or equal to. When it is the reverse way, what do we do? I'm going to show you that in this video with an example. So the next thing we do is to put our bounds. Okay, now I decide to have the bounds from minus infinity to infinity, but we said it's a non-negativity constraint, so we can as well use as 0 and then pass none. So we can define it this way. I want to remove that and define as 0 and pass none. So we have no upper bound. That's what it means. But our lower bound is to 0. X must not be less than 0, because it contains x will be greater than or equal to 0. Okay. So either ways, you can have it this way, or you can put a numpy dot infinity, which is goes, to the no bounds on the upper end. So we've done that. We run this cell, and then we call our solution to be minimized. Now call minimize, passing the function, passing an initial guess, just a guess, okay, initial condition for both variables as a tuple, and then set constraint to constrain, the bounds are the bounds. Okay, you can also look up the documentation of minimize on SciPy.org. If we run this, we already have a solution. Let's print the solution. If you print the solution, it gives us the message, optimization terminated successfully. We have found the solution. Success is true, status is 0. This is the optimal function. So at this point, x1 is 0 and x2 is 5. And number of function evaluation, number of Jacobian evaluation, all are listed there. So next we can print our solution, and what do we have? X1 is 0 and x2 is 5. So these two values makes this function optimal. Let's look at the second problem. In this problem, okay, we are looking at the chemical manufacturing firm, okay, that has discontinued production of a certain unprofitable product line. This has created considerable excess production capacity on the 3 existing batch production facilities that operate separately. Management is considering devoting this excess capacity to one or more of the 3 new products. Call them product 1, 2, and 3. The available capacity on the existing units, which my limit output is given in the table below. So we have the capacity A, B, C, okay, hours per week. Likewise, each of the 3 new products requires the following processing time. So to process the on the 3 units, we have product 1. These are the available processing time. So these are constraints. All we need to do is to abstract this problem and solve it. So the question says formulate the objective function and constraints. Now, if you look down here, we have been given some constraint that it says department indicates that sales for product 1 and 2 exceed maximum production rate, and the sales potential for product 3 is 20 batches per week. Their profit per batch would be $20, $6, and $8 respectively on product 1, 2, 3. So this profit forms the basis of our objective function. So now the question goes further to say how much of each product should be produced to maximize the profit of the company. So you see where we coin our objective function from. So solution, let x1, x2, x3 be the number of batches per week of product 1, 2, 3 respectively. So our objective function is defined as maximizing, okay, the profit, and the profit to be the profit per batch multiplied by the batches per week, and that will give us 20x1, 6x2, all summed together. What are our production capacity? Okay, on unit A, it says that what? On unit A was the production capacity 20 hours per week. So 0.8 of x1, 0.2 of x3, 0.3 of x3 should be less than or equal to 20. Okay, likewise, in this case, there is no productivity of batch 3, so 0.4 of x1, 0.3, and just do that subsequently to have here now we have all true inequality constraint less than or equal to. Now additional constraints do exist, as it says the sales potential. So sales potential of one product 1 and 2, sales potential, look at it here, it mentioned here, says the sales potential of 1 and 2 exceeds the maximum production rate. Okay, and while that of product 3 is that. So what's the maximum production rate? Maximum, where is it here? The maximum production rate, you can see it, 1.4 of x1 and 1.2 of x2 is greater than or equal to 35. That's what is mentioned here. It exceeds. So we come here. The sales potential, what was the total sales potential? 20, 10, 5. That's 35 of the 3 units. And 1 and 2 exceeds it. So product 1 and 2 will simply have 1.4, okay, and 0.5 of x2 greater than this sales potential for 1 and 2 exceeds total available time. So the total available time, okay, is 35 hours, while x3, okay, sales potential for 3 is 20 hours per week. So now we have additional constraint wherein we have an equality constraint present. So the non-negativity constraint do exist. Product 1, 2, 3 must be non-negative. So the optimization problem is fully formulated. Maximize this subject to this, right? How many constraints we have? 1, 2, 3, 4, 5. But we can minimize the negative of p. So minimizing negative of p automatically means maximizing p. So we'll write the problem by multiplying the function, the objective function, by negative. So we have, in this case, objective function becomes minus 20x minus 6x2 minus 8x3. Now, subject to, what we do here to also solve this problem, we convert all of these constraints. You see, okay, convert this constraint. This is inequality constraint with subject to set it to 0, subject to set it to 0, subject to set it to 0, and then here we transfer this. And then now all we simply need to do here is to even if you don't convert this to set this to 0, you can just what we simply do is to move this across here, and then less than or equal to 0 to set move it across, and minus 20 set to 0, move the values across, and that's all we have. If you don't set to 0, it's still less than or equal to, which is an inequality constraint. So here we define our function, okay, p taking x, and we have x1, x2, x3. And here we have assigned x1, x2, x3 to x of 0, x of 1, x of 2. And then we should return this. I just chose this convention to make it easier to write the function. The next, we define the constraint like we did earlier, and then, of course, passing all of these values, define the functions. What are the bounds? 0 to none, 0 to none, 0 to none, because we have 3 variables. Having done all of these, we have our problem fully formulated. The result is minimize p, and then we just make an initial guess. Okay, this guess can be any value, just make an initial guess, okay? And then set the constraints and the bounds. If we run the problem, we have a solution. Let's see our solution. We have, of course, it's telling us that x1 should be 25, product 2 should be 0, and should have 30 of product 3. So we can print out the detailed results to have something like this. Okay, to maximize the profit, the product should be produced as 25 of product 1, of course, 20 of product 2, and 0 of product 2 rather, and 20 of product 3. And the optimal profit is $660 if you produce this product on this mix. The third problem I will look at is to minimize an unconstrained optimization problem. So we want to minimize this function. So what do we do? In this case, we have to also import minimize scalar or root. There are 2 ways of doing it, which I'm going to show you. So the first way is, first of all, define your function and then call minimize scalar of f, and then, of course, apply the method Brent. You can look up this documentation of minimize scalar on SciPy.org, and then you see the various methods itemized there. If we run these and then call solution.x, it tells us the optimal value of x is 1.67. If you also want to see the optimal function, it's minus 12.67. Now, the next problem I have to talk about here is problem 4. I will not take time to read through these just to save the time, but I'll leave a link of this notebook, okay, to this video so that you can download it and then look through. But here we have 2 companies, affiliate companies, plants, A and B. A1 and A2 from which a given product is distributed to customers C1, C2, and C3. The transportation costs are given as follows. We have the various refinery and the customers alongside the transportation costs. The maximum refinery production rate and minimum customer demand rate are fixed and known to be as follows. So we have it also specified there. The cost of production of A1 is $30 per ton, and it is less than 0.5 ton per day. For production levels greater than 0.5 ton per day, the cost is this. A2's production cost is uniform. That's another constraint. So find the optimal distribution policy to minimize the company's total costs. So here we have a constraint optimization problem here, but also is a distribution problem. So you define Xij, let it represent the amount of product transported from refinery I to customer J. So the objective function is to minimize the total cost both of transportation and production. So the decision variables here are one, Xij, where I is 1, 2, and J is 1, 2, 3. In other words, we have 2 plants and we have 3 customers. Now, the objective function to minimize the total cost will be, I name it C, will be 25x11. Okay, cost of distributing to taking from plant 1 to customer 1, 60x12 from plant 1 to customer 2, 75xi3 from plant 1 to customer 3. Likewise, 20x21 from plant 2 to customer 1, plant 2 to customer 2, and plant 2 to customer 3. And all of these values are already detailed in the table, the various costs. Okay, so that's the objective function we want to minimize. Now, what is the refinery production constraint? We have x11x. So production from plant 1 to customer 1 and plant 2 to customer 1 must be less than or equal to 1.6. That's the maximum production rate. The maximum production from for plant 1 and for plant 2. So we have plant 1 first product, second product plant 2, and likewise for plant 2 we have this. Okay, then the customer demand constraint, we have in them specified here as we detailed in this table. Okay, that's the customer demand constraint. Of course, the non-negativity constraint Xij should be greater than or equal to 0. So for production cost constraint for A1, we have this. Remember, this is the demand constraint and the refinery production constraint. But for production cost, they said at 0.5 ton, he said when the cost of A1 is $30, production is less than 0.5 ton. When it is greater than 0.5 ton, it is $40. So that's another constraint. So when X11, X21 is less than 0.5, the production cost is what? A1 is 30 into the sum of the two. When it is greater, it is 40 multiplied by the sum of the two. But for A2, it is uniform, which is 35, X11, X12, X1, X12, X22, X23. This problem has to do with the distribution problem. We simply, import linear programming from SciPy to optimize. It's quite easier to solve such problem with it. So all we need to do here now is to abstract all the coefficients of these variables, okay, as vectors. First C, okay, takes out all the coefficients of the objective function, and likewise now we categorize as A, U, B. Abstract all of these constraints here. When we put this together, take out the coefficients of them. Okay, so this one stands for refinery production constraint. Next vector of this. Okay, so we create an array of those vectors, just like a list of lists. Okay, I call them list of lists, not really an array, is a list of lists. And B underscore UB is the value on the right side of the equality or inequality constraint. So that's why we have abstracted them as a list. Then the bounds, of course, how many variables do we have? Automatically we have 6. So I've created a 0 to none. Okay, and I multiply that list times 6 to produce 6 times of this element of 0 to none, which is a tuple. So the next I do is to call the results, and I'll call linear programming, passing the objective function AUB equals AUB, BUB equals B underscore UB, and then bound is X bound, and method I use height. There are other methods you can use in linear programming. And after that, I want to print the optimal distribution, print X11, X12, X and up till, and also print the optimal cost. If we run this, it gives us this. So these are the optimal distribution, okay, of the production across the plant and supply to the customer, and the optimal cost gives us about $93. The last problem here is considering a typical linear programming problem in which n grades of paper are produced on a paper machine due to raw material restriction, no more than AI tons of I grade produced per week. So here we say let Xi be the number of tons of grade I produced per week, let Bi be the hours of tons of grade I, and Pi be the profits. So of course we'll say because we have 160 production hours per week, the problem is to find the non-negative values of Xi, okay, subject to this constraint, and we're maximizing the profits. So here we're given the data table, okay, for AI, Bi, and Pi. So all we need to do is to formulate the problem. So this is a problem that we have formulated. Objective function, subject to this first constraint, we have 160 production hours. So all production hours, okay, multiplied by the various variables should be less than or equal to 160. And we have this constraint, okay, hourly, weekly, the constraint on each of the variables. So less than or equal to AI, and then those are this constraint. In same vein, we also, abstract that into a list. You can also use an array, okay, a NumPy array. It's going to give you the same results. And then we have AUB. This is the coefficient of all of the constraints, okay, on the left side of the inequality or equality constraint, and BUB, the coefficient on the right side of the inequality constraint. And then how many variables we have? We have 5 variables, so I create a bounds of 0 to none and multiply by 5. Notice what I've done here. I've used a tuple, and after the first tuple, 0 to none, I have a comma there. So this will create 5 of 0 to none instead of typing them manually. So the next is to call result linear programming like we did earlier, bounds and bounds. And so we print the optimal production, and then now the values are all lumped up in result.x. So if I now say for I, xi in the enumerate this, print the various results, and what do we have? You run that also. We have come here and run that. It prints our results x1, x2, x3, x4, x5, and the maximum profits is about $19,000. This, because of time restriction, I don't want to make this video too long. I will stop the video here. In the next video, I will take time to discuss and solve this problem, which involves the boiler turbo generator system optimization. Like my video, share my video, and if you are watching my video for the first time or you are a returning viewer, please subscribe to my YouTube channel, and I will see you in my next video. Bye.